Carefully, look through everything that's being said, and sort of like, let's just try and figure out how we can interpret every piece of information that's occurring. So, the first sentence: a tube is being stretched while maintaining its cylindrical shape. So we just have to imagine a tube, right? A tube in the shape of a cylinder, and this tube doesn't have ends, doesn't have it doesn't have the circular caps at each end. So it's just a tube. It might look something like this, right? And it doesn't have these caps on either end, right? So it looks something like this, and this is just nothing there, right? There's no cap. It's just this that has actual there's actual material there, and it's being stretched. So it could be that that's time one, and then sometime later it'll look like this, a little bit larger as you have that. Now, as it is that we stretch this tube, right? Okay, as it is that we stretch this tube, it gives us more information. So we're done. We have the idea in our minds of what's happening. This tube is being stretched, and it's maintaining its cylindrical shape. Now, the height is increasing at a rate of 2 millimeters per second. Now, the way it is that we interpret this next sentence. So here's the sentence. So this first sentence gave us some image of what's occurring. This tube is being stretched over time. So this is, time 0, whatever. This is maybe time 1. And it's going to keep being stretched at time 2, and so forth and so forth. Okay? Now, this next piece of information, it tells us that the height is increasing at a rate of 2 millimeters per second. The way it is that this sentence is interpreted mathematically is you say dH, the height is changing at a rate dt of 2 millimeters per second. dH dt. The derivative of h with respect to time is 2 millimeters per second. I'm just going to put 2. I'm going to leave out units. Now it gives us another sentence. So we've already interpreted this. We've interpreted 2 sentences. Now the third sentence, it says, at the instant that the radius of the tube is 6 millimeters. So at some time, right, at some point, there's the volume is going to increase, is going to be increasing at a rate of 96 pi cubic millimeters per second. So this gives us at some point dV dt, the rate of volume increasing, is 96 pi. And now it's asking us which of the following statements about the surface area of the tube is true at this instant. So now it then goes on in parentheses, and it tells us very relevant information. It tells us that the volume of a cube of radius r and height h is pi r squared h. And then it also tells us that the surface area of a cylinder is 2 pi r. Without the caps, which is the figure that we have. Okay, without the caps, not including the top and bottom. So they're calling this the top, and then this back piece the bottom, and we're not including that. So that's the surface area, right? The surface area is everything going around. So it's like if we cut it open, we would get like a rectangle. That would be the area of that rectangle would be the area of this. That would be the surface area of this tube. Now, if you look at each of these, it immediately says the surface area is increasing at some rate for each one, or decreasing. So it's talking about the rate at which the surface area is increasing, which is ds dt. Okay? So each one of these statements is asking essentially, what is ds dt? Okay? at this instant, at the time that the radius is 6 millimeters. Now, this here gives us all the relevant information to get the rate at which the surface area is changing, okay, the rate at which the surface area is changing, the rate at which it's increasing or decreasing at this particular time. Okay, and the way it is that you do this, okay, you need to know that V can be differentiated with respect to time. You're going to get dV dt. R can be differentiated with respect to time. You'll get dr dt. H can be differentiated with respect to time. You get dH dt. S can be differentiated with respect to time. You get ds dt. R can be differentiated with respect to time. You get dr dt. And again, okay? Now, you want to differentiate each of these formulas that they give you, because when you do, you'll see how it is that you can use that information to get this desired result, this ds dt, the rate at which the surface area is changing. You should see, though, if you're not sure, that the surface area is definitely increasing. I mean, they're saying that it's stretching, so everything should be getting larger. Everything is getting larger. It's asking that the volume is increasing. The surface area for sure should be increasing. So these two you could eliminate, and then you have a 50-50 shot at A or B. But let's see which one, whether it's A or B, because I don't know either. So now let's see. Okay, what we do here is we have to see this as dv, v, and r, and h as all functions of time, which means that you always want to be doing chain rule when you're differentiating things that are changing with respect to time, or any variables that are changing with respect to time. So r could be changing with respect to time. It's not clear whether they said that they're stretching this tube where this is the radius from the center to the edge right here. That's r, right? And I haven't done this yet. I don't know whether r is changing or not yet, because this new r, when we're stretching the tube, could be greater, but r could be staying constant, and we're just changing the height of this tube. This is 8. So it could be that over time h is just getting larger. But let's see. So now we have to remember again, r could be changing with respect to time, h could be changing with respect to time. But we need to know that always we do chain rule, right? So what does that mean? So the derivative of the volume with respect to time is just dV dt. That's just that one variable, dV dt, on the left-hand side. Now, pi is a constant that always can be just taken out. And then it's going to be times the derivative of r squared times h. And we need to know that this is a product. These two things are changing. Neither of them are constant as time goes on. So then therefore we have to be careful. We have to treat this as, when we differentiate, we have to treat this as a product rule. So the derivative of r squared with respect to time is 2 times r, because I bring down the 2 and I multiply by r to the first, times, and now I got to differentiate the inner part with respect to time, because look, it's r of t. R is some function. The radius is changing with respect to time, maybe, but if it's not, that's okay, because we'll compensate for that. So this is some function on the inside, and I'm differentiating with respect to time. This is the inner function, and then the squared part is the outer part. So I have it where it's 2 times this inner function to the 1 times the derivative of the inner function, dr dt. So then it's dr dt plus the derivative of h, just h, with respect to time, is dh dt times r. Oh wait, I forgot to multiply by h here. Sorry, times h. That's by product rule, right? So I have here that I got to multiply by the first one times the derivative of the other one. The derivative of h is dh dt. And I should move this parenthesis is wrong. Okay, forget about that parenthesis. It's just 2r dr dt times h plus r squared dh dt, and that's dv dt. Now, they give me that dv dt at a certain instant is 96 pi. So I have a value over here. But before I even start using this value, okay, so I have dv dt. All right, this is the, okay. I don't know what do I need to use it for. Well, let's see. I have dv dt. I'm not sure yet. Let's see. Now let's differentiate this one. Again, 2 pi is a constant that can come out times the derivative of r times h. And again, you have to use product rule. The derivative of r is dr dt. I'm going to put it, and then times h is h times dr dt plus the derivative of h is dh dt times r. So it's r dh dt. And now I have ds dt in terms of dr dt and dh dt and 2 pi. So let's see what I can do here. So now I have that when the radius, so when r, this dv dt is a function in terms of dr dt, dh dt, r, and h. Okay, so it's giving me that I have, let's see what I have. I have dh dt, I have dv dt, and then I have r. R is 6 millimeters, right? The instant the radius of the tube. So I have, what do I have in this formula? I have, let's go through what I have. I have, in this formula, I have dv dt. I have an r value. I do not have dr dt. I do not have an h value, but I have an r value, and I have a dht value. So let's see what I can get here. So now, how would I get dr dt? So the only thing that I can say is that, would it be the case? So let's see if I have to conclude that dr dt is 0. Is it true that dr dt is 0? That's the question we need to ask ourselves. So what information can we use to conclude that dr dt is 0? Because if it is, then I have all the information here. Well, let's see. So we have r. Well, the only thing. Oh no, I'm missing h. Okay, so h. How can I get h? So the height. When r is this. No, I need dr dt and h. Okay, let's see. So we have 96 pi is equal to pi times 2 6 dr dt, I don't know yet, times h plus r is 6 squared, and then dh dt is 2. And then now I can cancel out the pi's. 96 12h dr dt plus 36 times 2 is 72. And now I'm gonna minus this on both sides. I'm gonna get 96 minus 72, 424 is equal to 12h dr dt. And then I get 2 is equal to h times dr dt. And this is actually all I need, because now I have 2 is equal to whatever h is. I don't know what h is, and I don't know the rate at which the radius is increasing, right? So over time, the radius could be getting larger, it could be not, it could be 0. I don't know, but it doesn't matter, because now I have that h times dr dt. This is going to allow me, I know that 2 is equal to h times the rate at which the radius is increasing. That's all I need, because now if you look at this, right, I'm looking for ds dt at this instant. this same instant, I know that dh dt is 2. So I know this value over here is 2. So 2 pi. And then I know h times dr dt, right? I don't know what h is, and I don't know what the radius is increasing. But I do know that h times dr dt is 2. So this whole value is just 2. Plus r, I know the instant the radius is exactly 6. So this is 6. And then dh dt, I know the height is increasing at 2 millimeters per second times 2. And then this gives me 2 times 6 is 12, plus 2 is 14. 14 times 2 is 28. And I get here, again, ds dt is the rate at which the surface area is increasing. So I have ds dt is equal to 28 millimeters per second. And that means that it is choice A. Okay. So the tricky thing also was that I was trying to see if I could solve for one of the variables in this one, but they gave me an expression. And at the end of the day, I still don't even know whether the radius of this tube is increasing or not. I mean, it could be, well, no, it has to be increasing, because if this is 0, then there's no way 0 times h is ever going to give me 2. So the radius is increasing. Good. Okay, but I don't know what dr dt is. I know that dr dt times h always is equal to 2 for any time period, or for actually at that instant, the instant that we're talking about. But okay, we know that at this instant, the rate at which the radius is increasing times the height is equal to 2. And then I'm talking about that same instant over here. I want the rate at which the surface area is changing. And that's given by this derivative, ds dt. And I know h times dr dt was 2. So instead of writing that, I just wrote 2 in here. And then I knew the radius. They're talking about the radius that's 6. And then dh dt they gave us, right? I have this information. The radius was 6. They're talking about at the instant the radius was 6. So I put 6 here. And then I put what we got for dh dt, which is 2. They give us that. And then I just solved this for 28 pi. And then that's your answer.